In this video, we're continuing exercise 1328. We're going to go through D, E, and F. All right, the procedure here is the same procedure we've been working through, building up and practicing with in the last several videos. The first thing you want to do when you analyze these is to ask yourself if you need to form a new carbon-to-carbon bond. And usually that'll mean you use a Grignard reagent. As we saw in the previous video, the one thing that sometimes may make your life easier is if you have an alkyne, there may be a shorter way of making a new carbon-to-carbon bond than by using a Grignard. And so for a discussion of that, you might check out that video and that previous video for this exercise. But here, if you want to see whether you form a new carbon-to-carbon bond, then you would look at how many carbons you start with in your molecule. So 1, 2, 3, 4, with a sort of methyl group there. If you look in your product, you have 1, 2, 3, 4 with the methyl group, but you'll notice outside of that, we have a new carbon. And so the bond in between this blue and purple carbon chain, that's a new carbon-to-carbon bond. So we do form a new carbon-to-carbon bond, and so we will need to use a Grignard reagent here. And so we've gone through this process several times before. We can do a sort of retrosynthesis. We can start by looking at the product. Whatever carbon chain we want to add, that's the carbon chain that we're going to put in our Grignard. Where the bond connects to the carbonyl, that's where you put the magnesium bromide. So that's our Grignard. Now, when you do these Grignards, it's always in 2 steps. The first step is the Grignard reagent itself, and then after that, in a separate step, you want to do a water wash. And that's to stabilize the negative charge on the oxygen that forms when the Grignard reagent attacks. Now, you are going to be reacting these Grignard reagents with either aldehydes or ketones. The carbon chain that's left over, so everything except for what you're including in the Grignard reagent, so here, this light blue stuff, that's the aldehyde or ketone that you want to use. Now, I'm going to make sure this is an aldehyde. I don't want there to be a carbon here, because this carbon is what I'm adding from the Grignard, so I don't want it to be there originally. So I have this hydrogen here instead. And so this is going to be an aldehyde that I start with. Carbonyl, carbon double bonded to oxygen, with a hydrogen on one side. So that's an aldehyde. So if we react that Grignard reagent with that aldehyde, we do end up getting the carbon chain that we want. The only thing is, once this Grignard attacks, it breaks this pi bond, and so you only have one bond to the oxygen now. And that at first has a full negative charge. You do a proton transfer from the water, and it turns into an OH. So you have an alcohol. So you're really close to the final product you want, but you're not quite there. If you compare the 2 molecules, you'll see that in the alcohol, you only have 1 bond to an electronegative element. In the final product, you have 2. So the number of bonds to an electronegative element increased. That's oxidation. And so anytime you do oxidation, you have to ask yourself, should I use pyridinium chlorochromate in methylene chloride? Or should I use, and so this is a weak oxidizing agent, or should I use a strong oxidizing agent like sodium dichromate in water and sulfuric acid? So which one of those? Well, to answer that question, you have to look at what kind of an alcohol you have. Is it primary or secondary? Note that you would never be able to oxidize a tertiary alcohol. And that should make sense. If you go back to the videos where we discussed the mechanism for these oxidations, you'll remember that they're really elimination reactions. And so you always have to have a beta hydrogen to do those. And if you remember in these, the oxygen is like the alpha atom, the carbon next door is the beta atom, and if this is a tertiary alcohol, there are no beta hydrogens, so you wouldn't be able to do the elimination or the oxidation. So you're really only looking at primary or secondary alcohols. If you have a secondary alcohol, these oxidizing agents do the same thing. They turn it into a ketone. And so in that case, you can use either one. That's actually what we have here. If you look at the carbon that has the OH on it, it's bonded to 2 other carbons. So it's secondary. And if it's secondary, you can use either one of these. In practice, you would use sodium dichromate just because it's cheaper than PCC, pyridinium chlorochromate. The two oxidizing agents are different when you have a primary alcohol. PCC will take a primary alcohol to an aldehyde, and sodium dichromate in water and sulfuric acid will take it to a carboxylic acid. Okay, so here we had a secondary alcohol. We can turn it into this ketone by using any oxidizing agent. Here we'll use the cheap one, or the cheaper one, sodium dichromate in water and sulfuric acid. So far so good. We've sort of done a retrosynthesis. We saw our product, we were like, it has a new carbon-to-carbon bond, and we worked backwards to think about what we would need in order to form that. That's retrosynthesis, working backwards from the product. Okay, well now if we compare this molecule and the molecule we start with, these two have the same number of carbons. So it's just a matter of interconverting functional groups. So really we're going to want to go from an alcohol to an aldehyde. The one tricky thing here, though, is that these are on different carbons, right? This is on a carbon sort of in the middle, this oxygen is on the carbon sort of on the end. So we have to move the carbon. We have to move the oxygen. This oxygen needs to move over one atom, right, so that it's on the end. That means we have to take it off of this atom and add it on to the other atom, the other carbon. Well, to say that again, but in organic chemistry terminology, we have to take that OH off. That means we have to do elimination. And then we have to put this oxygen on. We have to add it. We have to do addition. So we're going to do an elimination reaction and then an addition reaction to move the oxygen from one carbon to the carbon next door, where we want it. Okay, elimination. The first thing with elimination is the OH is a terrible leaving group. And so now you could either do E1 or E2. You have a little bit more control with E2 because you could get either the Zaitsev or the Hofmann product with E2, whereas with E1 you only ever get the Zaitsev product as your major product. So let's go with E2. Now you can always see what you can get because the carbon that has the OH on it, if it's tertiary, then it has to be E1. If it's primary or secondary, if it's primary, it has to be E2. If it's secondary, it could be either. Now here it's secondary, right? The carbon that has the OH on it is bonded to two other carbons. So that alcohol is a secondary alcohol, and we technically have a choice between E1 or E2. But you have more control with E2. So that's what we'll do here. The first step for an E2 reaction is we have to turn that OH into a good leaving group. Right? It's a terrible leaving group right now. We have to turn it into a good leaving group, and we would do that by adding tosyl chloride, so that's TSCl, in pyridine. And we have the mechanism for that in a previous video. So what that does is it turns the OH into a tosylate. It turns the OH into an OTS, and this is now a good leaving group. So we had a bad leaving group, we turned it into a good leaving group. Now that we have a good leaving group, we can do an elimination. Now remember, anytime you do an elimination, the carbon that has the leaving group on it is called the alpha carbon. And any carbon bonded to that is the beta carbon. We have two beta carbons here. And so we can form a pi bond in two directions. We can do an elimination toward the left. And we can form a pi bond to the left. So we eliminate that, we form the pi bond to the left. Another option is we could do an elimination to the right. So we could take that same molecule and we could form the pi bond between the alpha and the beta carbon to the right. So our leaving group leaves and we form a pi bond between the alpha carbon and the other beta carbon. So these are our two possibilities when we're doing an elimination reaction on that molecule. Okay, so let's figure out how to classify these, and then we can figure out how we can control which one we get. If you look at the one on the left, look at the two carbons in the pi bond. Those have 1, 2, 3 carbon branches coming off of them. So that is tri-substituted. The other alkene, look at the 2 carbons in the double bond, that has only 1 carbon branch coming off of it. And so that's mono-substituted. Recall that the less substituted product is called the Hofmann product, and the more substituted product is called the Zaitsev product. Notice that this doesn't have to do with a specific amount of substitution. It's not that it's tri and mono, it's more substituted and less substituted. Okay, so those are our 2 options, and now that we have them clearly drawn and labeled, we can think about which one we want and how we can make sure we get it as our major product. We ultimately want the reactive part of the molecule to be toward the right. So we want the electrons to move to the right. If we do the elimination and the electrons move to the left, it's now the left part of the molecule that becomes reactive, but we don't want that. We want to add something to the right part of the molecule, so we want the right part of the molecule to become reactive. So we want the Hofmann product. Now you can control for the Hofmann product by adding a bulky base, like potassium tert-butoxide. And so that is what we'll have here. So we won't want to get this Zaitsev product as our major product, so we'll make sure that we use potassium tert-butoxide, and that will allow us to get this Hofmann product as our major product. Okay. So now that we have that alkene, now that we have gotten rid of this OH, we need to add an OH onto this other carbon, right? Remember our plan over here. We knew we had to eliminate the OH on this carbon in the middle, and we had to add an OH on this carbon on the end. Well, we've already done the elimination. Now we just have to do the addition. So what we'd really like, ultimately we'd like 2 bonds to an oxygen. We have to make those one at a time. So ultimately we'd like to take this alkene and add an oxygen onto the carbon on the end. So we would love if we could get this. Okay, well, there are several ways that you can add an OH onto a double bond. So to assess which one of those ways we need to use, let's think about where the OH added. Look at the 2 carbons in the double bond. We're going to think about whether they're mono, or they're primary, secondary, or tertiary. The carbon on the left is bonded to 2 other carbons, so it is secondary. The carbon on the right is bonded to just 1 other carbon, so it is primary. We want the OH to go on the less substituted carbon. That means we'd want the hydrogen to go on the more substituted carbon. If the hydrogen goes on the more substituted carbon, that is anti-Markovnikov addition. So we want to do anti-Markovnikov addition of H and OH. And there's only one way to do that, with hydroboration oxidation. So in your first step, you'd use 9-BBN. Second step, hydrogen peroxide, sodium hydroxide. And so now we have that OH on that less substituted carbon. So we're really close to this intermediate that we wanted. The big difference is that right now with this alcohol, there's only 1 bond to an electronegative element, and what we want has 2. If the number of bonds to an electronegative element increase, then that is an oxidation. And there are 2 oxidizing agents that you would want to use. The first option is pyridinium chlorochromate in methylene chloride. The second option is the strong oxidizing agent, sodium dichromate, in water and sulfuric acid. So which one of these should we use? Well, it depends. It depends on whether we have a primary or a secondary alcohol, and it depends on what we want that to turn into. So look at the carbon that has the OH on it. This is bonded to just 1 other carbon. So this is primary. If you have a primary alcohol, it really makes a difference which of these you use. PCC will turn a primary alcohol into an aldehyde. Sodium dichromate in water and sulfuric acid will turn a primary alcohol into a carboxylic acid. Which one do we want? The aldehyde. When you have a carbon double bonded to oxygen with a hydrogen on one side, that's an aldehyde. And so, to get that aldehyde, we want to use the weak oxidizing agent, pyridinium chlorochromate, in methylene chloride, CH2Cl2. And that completes this beautiful transformation. So what you'd want to write out is everything as a solution for full credit on an exam or on your homework is everything in this green box here. So what we did first was we saw that this OH, well, first of all, we approached this as a retrosynthesis and we worked backwards. Then we worked forwards and we met in the middle. So a very nonlinear problem type. It's like putting a puzzle together. You can put it together in many different ways. In many different orders, you can connect the different pieces. So what we did is we saw this OH here needed to get off of that carbon because it's not on that carbon in the products. So we turned the OH into a good leaving group, and then we did an elimination reaction. We wanted the pi bond to form toward the right because that's where we ultimately wanted this oxygen to be. So we used a bulky base to get the Hofmann product. Once we had that, we did anti-Markovnikov addition of H and OH, hydroboration oxidation. That gave us a primary alcohol, which we could turn into an aldehyde using PCC and methylene chloride. Once you have that aldehyde, we used a Grignard reagent to add the new carbon-to-carbon bond, and you can oxidize that to get this ketone. Okay, so much for D. How about E? All right, in this one, we'll follow that same process of thinking as we've been practicing. First, do we form a new carbon-to-carbon bond? Now, here, what we have is a 5-membered ring with 2 carbons attached to it. On the other molecule, in the products, we have a 5-membered ring with two carbons attached to it still. But then you have a 3rd carbon. So the number of carbons increases, and this bond here between the purple and the blue carbon chains is a new carbon-to-carbon bond. Okay, so we do need to form a new carbon-to-carbon bond. And you may be tempted, at first, maybe you see this alkyne, you may be tempted to do the alkyne reaction we saw in the previous example. And you can always try it. And the truth is, with these synthesis problems, the only thing you could do completely wrong is nothing, right? The best thing, even if you're completely stuck, try something. Maybe it'll help you to see a new connection you didn't see before. So even if it leads to a dead end, it's worth trying something because maybe it allows you to see a new connection that you didn't see before. Now, if you did try to do this with the terminal alkyne reaction we learned reviewed in the previous video, you might run into a little trouble that way. This actually ends up being a little more straightforward and quicker if you do the Grignard reagent, like you would expect for this chapter. So let's try doing that Grignard reagent. So what we can do to get this Grignard is we look at the new carbon chain that we want to add. That's what we're going to make the Grignard reagent out of. Where it attaches, that's where we write in the magnesium bromide. So that's our Grignard. Now, Grignard reagents are always added in 2 steps. First the Grignard, and then a water wash to stabilize the negative charge that forms on the oxygen. And we always need an aldehyde or a ketone to react that with. Oops. And so, if we had this aldehyde, right, and notice I replaced that bond there, the one that is going to go to the carbon, here it's going to just a hydrogen because the carbon is not attached yet. So I take that aldehyde, I react it with a Grignard, and I get an alcohol. So the carbon bonds have formed, but in the process the pi bond broke, and you'd have an OH there. And if that doesn't make sense, I strongly encourage you to review the video from this chapter for making alcohols with Grignard reagents. Now once you have that, we're not quite at the final product, but we're close. We're very close. And so to get that, the only difference between those two is the number of bonds to the oxygen. This has 1, the final product has 2. If the number of bonds to an electronegative element increases, that is an oxidation. And so here we're going to want to do an oxidation. And so we have two choices. We can either use the weak oxidizing agent, PCC, in methylene chloride, CH2 or Cl2. Or we could use a strong oxidizing agent, and that would be something like sodium dichromate in water and sulfuric acid. Well, which one of those we use depends on what type of alcohol we have and what we want. So look at the carbon that has the OH on it. Here it's bonded to 2 other carbons. That is a secondary alcohol. And both of these oxidizing agents do the same thing to a secondary alcohol. They only do different stuff to primary alcohols. PCC would turn a primary alcohol into an aldehyde. Sodium dichromate in water and sulfuric acid would turn a primary alcohol into a carboxylic acid. Because we have a secondary alcohol, we could use either one, and in practice you would use the cheaper one, which is sodium dichromate in water and sulfuric acid. And that will turn that secondary alcohol into a ketone. Okay, so far so good. But now we have this aldehyde, whereas what we need to start with is this alkyne. Can we turn an alkyne into an aldehyde? And we can. If you look at that chart for functional group interconversions that we built up in a previous video, you'll notice that we can turn an alkyne into an aldehyde by doing either an acid-catalyzed hydration or hydroboration oxidation. And that just depends on where you want the oxygen to add, whether in a Markovnikov or an anti-Markovnikov way. So here, look at the 2 carbons in the pi bonds. This one on the end is only bonded to 1 other carbon, so that's primary. The one in the middle is bonded to 2 other carbons, so that is secondary. We want the oxygen to go on the end, so that is going to be we want the oxygen to go on the less substituted carbon, and the hydrogen to go on the more substituted carbon. If the hydrogen goes on the more substituted carbon, that is anti-Markovnikov addition. So we'll want to do the anti-Markovnikov addition, which is hydroboration oxidation. So the first step would be 9-BBN, and the second step is hydrogen peroxide and sodium hydroxide, H2O2 and NaOH. And what this does is it adds an OH onto this anti-Markovnikov, and then you get ketoenol tautomerism so that it rearranges to the aldehyde. And if you don't remember from Organic Chemistry 1 what ketoenol tautomerism is, I strongly recommend you watch the review video for that in the Organic 1 playlist. That will come back later in the semester in a really huge way, toward the end of the semester. So it's a good thing to review. It'll make your life easier in the future. Okay, and that would be a complete synthesis for this exercise. So you can turn this alkyne into an aldehyde by doing hydroboration oxidation. Then you can add a new carbon using a Grignard reagent, and then just oxidize that alcohol using a strong oxidizing agent. So you'd want to include each of those things, each of the reagents and the intermediates, in the solution you draw on a test or a homework or an exam. All right, let's try F. This is the last one for this homework. After this, go celebrate, go relax, go reward yourself. You've completed the homework set. Pat yourself on the back. You should feel really proud. Okay, so what do we see here? First, do we need to form a new carbon-to-carbon bond? Well, on the left we have 3 carbons. On the right we have the same 3 carbons, but attached to them we have this one last carbon there. And so we do need to form a new carbon-to-carbon bond between the blue and purple carbon chains here. Okay, so how can we do that? Well, we can take the carbon chain that looks different and make our Grignard reagent out of it. So where it attached to the other carbon chain, we're going to put the magnesium bromide. Now, you always use these Grignard reagents in 2 steps. First is the Grignard reagent itself. Second is a water wash to stabilize the negative charge that you get on the oxygen after the Grignard attacks. And to get these, we need an aldehyde or a ketone. Now that we're going to get from the chain that was left over, that blue chain. Now right now it's an alcohol, we need an aldehyde or a ketone, so we're going to erase that hydrogen and draw in the carbonyl. So this ketone. And this is actually acetone. You may have used it to take off nail polish. So if you take acetone, you react it with this Grignard reagent and water, you do end up getting this alcohol. Now notice we don't have to oxidize it like we've been doing in previous exercises because we don't end up with a ketone. We end up with the alcohol. That's what we want in F. We want the alcohol, so we just do that and the Grignard's done. Now we just need to connect this to our starting material. They both have the same number of carbons. Where they're different is the number of bonds to the oxygen. Our starting material has just 1. This acetone molecule has 2. If the number of bonds to an electronegative element increases, then the type of reaction is oxidation. And we have 2 oxidizing agents that you would want to consider. The first is pyridinium chlorochromate in methylene chloride, and the second is sodium dichromate in water and sulfuric acid. Okay, now which one of those we use depends on what type of an alcohol we have and what we want it to turn into. So look at the carbon that has the OH on it. That's bonded to 2 other carbons. So that is secondary. And with secondary alcohols, it really doesn't matter. You could use either of those oxidizing agents and I would consider it correct. They both oxidize secondary alcohols into ketones. So in practice, what you would do is you'd use the less expensive one, and that turns out to be sodium dichromate in water and sulfuric acid. So Na2Cr2O7 in water and sulfuric acid, bada bing, bada boom, you're done. This one wasn't so bad, right? You do that oxidation, you get the ketone, and then you do the Grignard reagent, followed up with some water, and you've got your product. And that beautiful recipe would be what you would want to write down with all the intermediates. And don't forget the numbers in front of reactions if you ever do them in pairs, like with a Grignard reagent and water. So that's what you'd want to write in your answers for this on an exam. All of that. Now, in these examples, these multi-step syntheses, I have shown you at least one way to reason through the question, one possible synthesis. But like I said, these are nonlinear problems and they have many ways they can be solved. So if you came up with a way that I didn't cover in the video, and you just want to make sure it's correct, come meet me in my office hours. I would be delighted to go over that work with you. I would be delighted to see your awesome thought and to tell you what's good about it and what may be mistaken about it, and to help you on your way. So these synthesis exercises will be with us for the rest of organic chemistry. So the time you put in now will really pay off. It's a good investment to make to master this thought process and to master the reactions that we've gone over. And otherwise, that's the end of this chapter. You should reward yourself with a gigantic bowl of ice cream or something. Thank you so much for your attention, watching all these videos for chapter 13, and I will see you in class.